Oh, g'day, Mr. Bennett here again. Today we're just going to be looking at another example to do with Coulombs Law. Alright, so remember this is the second video that we're doing on this. So just a reminder about the formula, Coulombs Law, which is force equals 1 over 4 pi epsilon, Q1 over Q2 divided by R squared. Now, obviously constant value is 9 by 10 to the 9. We know that Q is the charge of an object. Alright, so we're looking at that. Now, we also can find this relationship, so the force is directly proportional to Q1 and Q2, which is really important that you get your head around this, and the force is inversely proportional to the radius squared. Now, we also have looked at this particular example over here, which is force gravitational is equal to the gravitational constant and the product of the two masses over the radius of the centre squared. Remember we were talking about satellite motion. See how these sort of two forces relate to each other. Obviously this could be on a grand scale or on a micro scale. This again could be on a grand scale or a micro scale. So these laws work no matter what situation we're looking at. Now, interesting, I want to talk about in terms of an atom. So if you're thinking about an atom, and obviously this is not the most important part of the topic, but just to get your head around this. Now, through many years of research and development, obviously physicists have actually come up with our present model of the atom, which we have a positive nucleus. In there we have protons and neutrons, and orbiting around that we have electrons. So we have electrons at different set shells, and you might have done that in junior science, alright? Or if you do chemistry, you certainly would know about that. Now, I just want to give you the perspective about the atom itself, which is, if you imagine a pea like a little green pea being in the middle of our oval, the first electron shell would be orbiting around the boundary line of the oval itself. So it gives you a perspective of the size of that. So what do we know really necessarily about that in terms of itself? Well, if that is the nucleus, that's got most of the mass of the atom, and the electron running around the edge of the boundary line, that means that there's a lot of space in here. So 99% of, well, even probably more of that, of an atom is actually made up of space. Right? So you could say to someone, well, you're made up of atoms, and that's all we are. We're made up of atoms. And then we start looking at you as a person. Well, technically, if you're made up of these atoms and they're 99% space, you could say to someone, well, you're really 99% space. Interesting to think about that is when you start looking at the idea of a black hole, which is simply a collapsed star, got massive gravity in there. So if you think about how heavy you are and for the size of your particular body, well, 1 teaspoon of matter in a black hole is in fact equal to about 10 tonne. Alright, so you get the idea, the density of that particular stuff. So we're looking at atoms. Now, obviously, with Coulombs Law, that relates to these things here. Okay, we've got Coulombic forces between the positive nucleus and the electron shell. Alright, so the charge of electrons is fairly small, 1.6 by 10 to the minus 19, and if you look at the mass of electron, it's 9.11 by 10 to the minus 31 kilograms. Alright, the proton is a lot heavier, it's about 4 times heavier than an electron. Alright, and that's why we say generally an atom is made up of the mass really of the protons. Now the other units that you would have found, now all of these constants are on your formula sheet, and these ones also are on your formula sheet. So we use micro for 10 to the minus 6, we use nano for 10 to the minus 9, and we use pica, so picocoulombs for 10 to the minus 12. Now you don't need to remember them, as I said, they're on your formula sheet, but that's how you can actually prefix things if you see those. Just want to look at another example of Coulombs Law. Obviously, we won't worry about this first one. That's just simply using the formula as per that. The interesting question here is, let's say we have two positive charges, and one's got a charge of 3.6 microcoulombs, and the other one's got a charge of 4.5 microcoulombs, and they're 50 centimetres apart. If we put something obviously at the 20 centimetre mark and minus 5 microcoulomb charge, what would be the overall force on that? Alright, so obviously if we're looking the effects of the 3.6 microcoulomb charge, and this is a good idea of using a prefix, so you put everything in there, so you get the 5 microcoulomb, the 3.6 microcoulomb, and it's 20 centimetres apart. That will actually cause a overall force of 4.05 newtons. Now, because it's negative and that's positive, it's going to pull it to the left. Okay, so you've got to give the force in the direction. The overall effect of the 4.5 microcoulomb, again, is 2.25 newtons, and that's going to be to the right. So what we've got over here is a vector addition. Okay, we've got to do a vector addition. So we've got the one going to the right, which is 4.5. We've got this one going to the left, which is 2.25. So the overall force will be that this one goes to the left at 1.8 newtons. Okay, so that's the overall effect of that. Hopefully that makes sense. Alright, now this question here is a little bit different. Okay, this question says, where should I put the 1 Coulomb test charge? Now if we don't know what the charge is, we always make it a plus 1 Coulomb test charge so it doesn't move. Okay, giving it that's 5 nanocoulombs and that's 7 nanocoulombs. Alright, so what we want to do is we want to have the force pushing that way and the force pushing that way to be equal to 0. So these two vectors that would be from here and from here have to be the same. They're both going to be repulsion. Alright, so this is what we're going to do. Okay, we're going to set this up with the two forces have to be equal. So we can get rid of this constant value straight away. That's not going to need to be there. We're using a 1 Coulomb test charge. And what we're saying is the distance between these two charges, if we're going to call this distance here x, then this distance here is going to be 1 take x. Got the idea? Alright, because we know they're 1 metre apart, those two things. So if we do that, now this is the idea of using a ratio. Okay, now if we start using these 10 to the minus 6s, you can do it like that. But really, these charges are in a ratio of 5:7. Okay, and that's going to be x squared, and that's going to be 1 take x squared. So this actually becomes a mathematical question. Alright, and we're just going to use quadratics to solve this. So this up the top line, we cross multiply to get rid of the fraction. So that's going to be 5, 1 take 2x plus x squared. That's going to be 7x squared. So then what we can do is we can rearrange this equation, can't we? So bring the 7 across, or bring this across to the side over here. So 7x squared take 5x squared is going to give me 2x squared. That negative 10x is going to become plus 10, and the plus 5 is going to become negative 5. Now if you factorise it on your graphics calculator, you'll get the distance of x being obviously either negative 5.46 or 0.46. Now obviously it can't be negative 5.6 because that means it's actually outside of the metre. So it's going to be 0.46 metres. So therefore that's how far from the 5 Coulomb charge that we're going to need to be. Alright? Interesting concept, but you know, it's not that hard. It's just using a ratio and equating the two forces. Now, I'll show you some other interesting ideas as well in terms of using ratios for Coulombs Law. Alright, so keep going with those questions and I'll catch you in class.